How to implement multi-threading in Python. Hey everyone, welcome to the Code Wizard. We're excited to share our latest tutorial on how to implement multi-threading in Python. If you're new to our channel, make sure to hit the subscribe button and turn on notifications so you never miss a video. And if you're enjoying the content, don't forget to give us a thumbs up. Let's dive into today's topic and unlock the magic of programming together. In Python, you can use the threading module to implement multi-threading. The thread class of the threading module provides a way to create a new thread in your program. Here is a simple example to demonstrate how to use multi-threading in Python. Python, copy code, import time, import threading, def worker, num, thread worker function, print, thread, is running, format, num, time, sleep, 1, print, thread, has finished, format, num, hash create two threads, threads equals, for I in range, 2. T equals threading, thread, target equals worker, args equals, I, threads, append, T, hash, start the threads, 4. I in range, 2. Threads, I, start, hash, wait for all threads to finish, 4. I in range, 2. Threads, I, join, print, all threads have finished. In this example, we defined a worker function that takes an argument num and prints out a message indicating the thread is running and a message indicating the thread has finished. Then, we create two threads using the thread class, start the threads, and wait for all threads to finish using the start and join methods of the thread class. In addition to the basic thread class, the threading module also provides a number of other useful classes and functions for implementing multi-threading in Python. For example, lock. A lock is a synchronization primitive that can be in one of two states, locked or unlocked. A lock is created in the unlocked state. It can be locked using the acquire method and unlocked using the release method. Locks are useful for ensuring that only one thread at a time accesses a shared resource. Rlock. A reentrant lock is a lock that can be acquired multiple times by the same thread. This can be useful when a thread needs to lock a resource, perform some actions, and then lock the resource again. Semaphore. A semaphore is a synchronization primitive that tracks a count. A semaphore is created with an initial count. The acquire method decrements the count and blocks if the count is 0. The release method increments the count. Semaphores are useful for limiting the number of threads that can access a resource. Event. An event is a synchronization primitive that provides a way to communicate between threads. An event is created in the clear state. The set method sets the event, and the clear method clears the event. The wait method blocks until the event is set. Events are useful for signaling between threads. Here is an example that demonstrates the use of locks, semaphores, and events in Python. Python, copy code, import time, import threading, counter equals 0, counter underscore lock equals threading, lock, counter underscore semaphore equals threading, semaphore, 3, counter underscore event equals threading, event, def worker, thread worker function, global counter, with counter underscore semaphore, with counter underscore lock, counter plus equals 1, time, sleep, 1, with counter underscore lock, print, thread, has finished, format, counter, counter underscore event, set, hash create 10 threads, threads equals, for I in range, 10. T equals threading, thread, target equals worker, threads, append, T, hash start the threads, for I in range, 10. Threads, I, start, hash wait for all threads to finish, for I in range, 10. Counter underscore event, wait, counter underscore event, clear, print, all threads have finished. In this example, we created a global counter, a lock for the counter, a semaphore for limiting the number of threads that can access the counter, and an event for signaling between threads. The worker function increments the counter, waits for 1 second, and then prints out a message indicating the thread has finished. The worker function is executed by 10 threads, which are created, started, and waited for using the thread class. The counter is protected by the lock in the semaphore, and the worker function signals the event after it has finished. Step by step. Explanation. The implementation of multi-threading in Python step by step. Step 1. Import the threading module. Python. Copy code. Import threading. Step 2. Define a worker function that will run in a separate thread. This function can perform any desired actions. Python. Copy code. Def worker. Thread worker function. Hash your code here. Step 3. Create a thread object and pass the worker function as the target argument. You can also pass any arguments to the worker function using the args argument. CPP. Copy code. Thread equals threading. Thread, target equals worker. Step 4. Start the thread by calling the start method of the thread object. CPP. Copy code. Thread, start. Step 5. Optional. Wait for the thread to finish by calling the join method of the thread object. This will block the calling thread until the thread has finished executing. CPP. Copy code. Thread, join. Step 6. Optional. You can create multiple threads by repeating steps 3 to 5 for each additional thread. Here is the complete code. Python. Copy code. Import threading. Import time. Def worker. Thread worker function. Print, thread is running. Time, sleep, 1. Print, thread has finished. Thread equals threading. Thread, target equals worker. Thread, start. Thread, join. Print, main thread has finished. This code creates a single thread and starts it. The worker function prints a message indicating the thread is running, waits for 1 second, and then prints another message indicating the thread has finished. The main thread waits for the worker thread to finish by calling the join method, and then it prints a message indicating that the main thread has finished. Note that in this example, the worker thread is executed in parallel with the main thread. However, because the main thread calls join to wait for the worker thread to finish, the program will not continue until the worker thread has finished. You can also create multiple threads in the same program and have each thread run its own worker function. Here is an example that demonstrates this. Python. Copy code. Import threading. Import time. Def worker 1. Thread 1 worker function. Print, thread 1 is running. Time, sleep, 1. Print, thread 1 has finished. Def worker 2. Thread 2 worker function. Print, thread 2 is running. Time, sleep, 1. Print, thread 2 has finished. Thread 1 equals threading. Thread, target equals worker 1. Thread 2 equals threading. Thread, target equals worker 2. Thread 1. Start. Thread 2. Start. Thread 1. Join. Thread 2. Join. Print, main thread has finished. In this example, 2 worker functions are defined, and 2 threads are created, each running its own worker function. The main thread starts both threads and then waits for both threads to finish by calling the join method on both threads. Finally, the main thread prints a message indicating that it has finished. It's worth noting that the order in which the worker threads run and finish is not guaranteed and may vary each time you run the program. This is because the operating system schedules the execution of threads, and it is not possible to determine exactly when each thread will be scheduled to run. Another important aspect of multithreading in Python is thread synchronization. This is necessary when multiple threads need to access the same resources, and it is important to ensure that these resources are not corrupted. The threading module provides several mechanisms for synchronizing threads, including locks, semaphores, and conditions. For example, consider a situation where you have a shared resource, such as a list, that needs to be updated by multiple threads. Without proper synchronization, it is possible for one thread to access the list while another thread is in the middle of updating it, leading to inconsistent data. To prevent this, you can use a lock to synchronize access to the list. Here is an example that demonstrates this. Python. Copy code. Import threading. Import time. Shared underscore list equals. Lock equals threading. Lock. Def worker 1. Thread 1 worker function. With lock. Print, thread 1 acquired lock. Shared underscore list. Append. 1. Time. Sleep. 1. Print, thread 1 released lock. Def worker 2. Thread 2 worker function. With lock. Print, thread 2 acquired lock. Shared underscore list. Append. 2. Time. Sleep. 1. Print, thread 2 released lock. Thread 1 equals threading. Thread, target equals worker 1. Thread 2 equals threading. Thread, target equals worker 2. Thread 1. Start. Thread 2. Start. Thread 1. Join. Thread 2. Join. Print, shared list. Shared underscore list. Print, main thread has finished. In this example, a lock is created, and the worker functions acquire the lock before updating the shared list. When a thread acquires the lock, other threads that attempt to acquire the lock will be blocked until the lock is released. This ensures that only one thread at a time can access the shared list, avoiding any potential inconsistencies. I hope this provides a good starting point for implementing multi-threading and improve the performance and scalability of your programs, and I encourage you to explore it further. Thanks for watching our tutorial on how to implement multi-threading in Python. We hope you found it helpful and informative. If you did, make sure to hit that like button and share this video with your friends who are also interested in how to implement multi-threading in Python. And don't forget to subscribe to our channel for more tutorials, tips and tricks on Python programming and scientific solutions. Thanks for being a part of the Code Wizard community, and we'll see you in our next video.